in beam design. Welcome to Blueprint to Reality, where we transform engineering concepts into clear, easy-to-understand explanations. Today, we explore the fundamental differences between point loads and distributed loads in beam design, how they influence structural behavior, and why engineers must carefully consider them in construction. Understanding these forces is essential for designing safe and efficient buildings, bridges, and other structures. Definition of point load. A point load, also known as a concentrated load, is a force applied at a single, specific location along a beam. This type of load does not spread across the length of the beam, but instead acts at one point, creating localized stress. Point loads are common in structural engineering, often occurring when a heavy object or structural component, such as a column, machine, or vehicle wheel, transfers force onto a beam. These concentrated forces lead to high internal stresses, which can result in bending, shear failure, or even localized crushing of the beam material if not properly designed. For example, in a bridge, the wheels of a truck apply point loads on the structure as they move across. Similarly, in buildings, a beam supporting a column or a mechanical unit must be designed to withstand significant point loads at those locations. Engineers often reinforce these points with additional materials, such as steel plates or deeper beam sections, to prevent excessive stress concentrations. Definition of distributed load. Unlike a point load, a distributed load is spread over a length of the beam rather than being concentrated at a single location. These loads can be classified into two main types. 1. Uniformly distributed load, UDL, a load that is evenly spread across a beam's length. Each section of the beam carries the same load intensity, leading to a more gradual stress distribution. A common example is the weight of a floor slab resting on a beam or water pressure in a tank wall. 2. Non-uniformly distributed load, varying load, a load that changes in intensity along the beam. For example, wind pressure on a high-rise building facade varies depending on height and exposure. Another example is snow accumulation on a sloped roof, where the load is heavier at the lower sections. Distributed loads reduce localized stress concentrations, making the beam less vulnerable to sudden failures. However, they require a different approach in beam design, ensuring the structure can handle the cumulative effects of the load over its entire span. Effect on bending moment. The bending moment is a critical factor in beam design, as it determines how a beam bends under load. The type of load applied significantly impacts the bending moment distribution. Point loads create sharp peaks in the bending moment diagram, leading to localized high-stress areas. The bending moment increases suddenly at the location of the load and decreases beyond it. This sharp variation means the beam must be stronger at specific points to prevent failure. Distributed loads produce smoother, more gradual bending moment curves, distributing forces more evenly. Instead of a sudden peak, the bending moment gradually increases and decreases across the beam, reducing stress concentrations. This even distribution allows engineers to design beams that efficiently handle weight without unnecessary material usage. Understanding how these loads affect bending moments helps structural engineers determine the optimal beam size, reinforcement placement, and material selection. Stress distribution. The way forces are spread through a beam determines its overall performance and durability. Point loads cause high localized stress, making the material near the load more susceptible to failure. Cracking, shear failure, or crushing of the material may occur if the beam is not reinforced adequately at these locations. Distributed loads create a more uniform stress distribution, allowing the beam to carry heavier weights without developing excessive internal stresses in one particular spot. This makes distributed loads easier to manage from a structural standpoint. For example, a beam supporting a row of bookshelves, distributed load, experiences gradual stress, while a beam supporting a hanging chandelier, point load, experiences a sudden stress concentration, requiring extra reinforcement around the hanging point. Structural design considerations. Since point and distributed loads behave differently, engineers must adjust beam design accordingly to maintain stability and safety. For beams subjected to point loads, structural engineers reinforce specific points by increasing beam depth, adding steel plates, or using stronger materials. They also use stiffeners and shear reinforcement to counteract localized forces. For beams subjected to distributed loads, the entire structure must be designed for uniform stress resistance. This often involves optimizing beam cross-sections, spacing support strategically, and ensuring deflection limits are within acceptable ranges. An example of this consideration is bridge design. Engineers must account for both the point loads of moving vehicles and the distributed loads of the bridge deck's own weight. Real-world applications. Understanding point and distributed loads is crucial in various engineering fields. Here are a few examples. Buildings. Floor beams must handle point loads from walls and columns while also supporting distributed loads from flooring materials and occupants. Bridges. Moving vehicles exert point loads, while the weight of the bridge deck and railings apply distributed loads. Roofs. Snow accumulation acts as a distributed load, while air conditioning units or antennas exert point loads. Each scenario requires different beam reinforcements to ensure safety and longevity. Failure risks and mitigation. Both load types come with risks that engineers must mitigate through careful design. Point loads increase the likelihood of shear failure, bending failure, or cracking at specific locations. Engineers counter this by strengthening those points with additional materials and reinforcement. Distributed loads, if excessive, may cause beam deflection, sagging, or buckling over time. Proper material selection, cross-sectional adjustments, and bracing techniques help prevent these issues. For instance, in high-rise buildings, engineers place additional reinforcements at beam column junctions where high point loads occur, while using continuous beams for floor structures to evenly distribute forces. Conclusion. Point loads and distributed loads play a crucial role in structural design, each with unique effects on beams. While point loads create localized stress concentrations, requiring reinforcement at specific locations, distributed loads spread forces more evenly, reducing stress spikes. By understanding how these forces interact with structural materials, engineers can design safe, efficient, and cost-effective buildings and bridges. Thank you for watching Blueprint to Reality. If you enjoyed this in-depth breakdown, be sure to like, subscribe, and stay tuned for more insightful engineering content. See you in the next video.